No. I think it's muted.
No. Yes.
Okay. So can you hear me now?
Yes, very good.
Okay.
Okay, so yeah, Alberto will do the last lecture on GW in practice, and I think the focus will be on 2D materials.
Yeah, so I will have like two, so the lecture is divided in two. In the first part, I will explain, so the first one is called G0, W0 in practice, and I will show the practical equations which are numerically solved within the Yambo code, and this is a small part. Then in the main second part, I will talk about the G0, W0 on two-dimensional systems. So I'm Alberto Guandalini, and I'm a postdoc at CNR-NANO in Modena. So let's start from Hedin's equations, these 5 here. And here we have the Feynman diagrams, which correspond. I will go quite direct in this part because this has already been explained. So the main point here is that if you are able to solve self-consistently all of these equations, you're going to have the true G, which pose corresponds to the quasi-particle energies. But of course, this is very difficult. And this is mainly due to the fourth equation, that is the equation for the vertex function. Then what we can do is just to neglect vertex effects, and this makes the self-energy to be written as the famous GW, and this is why this is called the GW approximation. While for the screened interaction, we have a correspondent RPA approximation. Then we would solve self-consistently these equations here for the G that is also employed in the polarizability and the self-energy. But what is usually done in practice is not to solve self-consistently the interacting Green's function within this equation, and this brings us to the G0, W0 approximation. This is because G0 is employed in the calculation of the polarizability, which brings to W0, and also this G here is computed with the independent particle approximation. So what Yambo implements in practice is more or less these 5 equations here written in a more numerically explained picture, as we will see. Of course, the fourth equation is trivially solved. So the main goal of this part would be to see which are the corresponding of these equations here, and this in order to deeply understand which are the main approximations involved also in practice, and also which are the main convergence parameters that should be taken under control. Okay. But first of all, it's important to comment also on the basis set representations. All these operators here should be represented on a basis function in order to become numerical matrices and in order to be represented. So Yambo uses 2 different sets of basis functions. The first one is plane waves, as in quantum espresso. And the second one is Kohn-Sham states that are taken as an input from quantum espresso. And we can see that all of these quantities here can be conveniently represented in one of the 2 spaces. For example, the Coulomb interaction is diagonal in plane waves, while it depends on 4 indexes in the basis of Kohn-Sham states. And as the opposite, the G0 is diagonal in the basis of Kohn-Sham states, while it depends on GG prime and Q in plane waves. Thus, what Yambo does is to solve the dielectric properties in plane waves, then to compute one element of the self-energy in Kohn-Sham states, and this is an approximation, as we will see in the next slide. Then there are the matrix elements to change from one base to the other, that are these ones here. And it's also important to notice that in practice, we are going to cut off the basis function Thus, the two important parameters that should be converged are the number of plane waves, which are usually controlled by an energy cutoff, as again in quantum espresso, and a finite number of Kohn-Sham states, while the complete Hilbert space would be represented with an infinite number of Kohn-Sham states. Okay. So how to solve the Dyson equation for G? Here we have the diagrammatic representation and also the Dyson equation. Okay, so the pointer is strange. And with the Lima representation for the interacting G, we can rewrite this Dyson equation in an Hamiltonian formulation. That is an eigenvalue equation for the quasi-particle energies, which are the eigenvalues, and the quasi-particle orbitals, which are the eigenvectors. This is kind of a difficult equation to solve. Then the quasi-particle approximation is usually employed. And this corresponds to suppose that the quasi-particle orbitals can be conveniently approximated with the Kohn-Sham orbitals. This is not always true, but this is usually implemented. Thus, one has to keep in mind whether this approximation is good or not. This brings an eigenvalue equation to just an equation for the eigenvalues, in which we have a correction to the Kohn-Sham eigenvalues given by the self-energy. Thus, in order to obtain the quasi-particle eigenvalues here, we just need to evaluate the self-energy at a certain energy. Then, usually, this equation is solved within the Newton method, in which the self-energy computed at the quasi-particle energy is Taylor expanded along the Kohn-Sham energy. Then we need to evaluate the first order coefficient that is usually computed with the finite differences method. This is thus the goal of a G0 W0 calculation, which requires to compute mainly the self-energy at two different frequencies. One is at the Kohn-Sham eigenvalue, and one is on a slightly shifted frequency in order to compute the first order coefficient of the Taylor expansion, thus these which are called zeta coefficients. So this is the goal, and in order to reach the goal, we need to compute the screened interaction. As we said, this is computed in G space, so W. And we start from the irreducible polarizability, which is a bubble diagram. This is the expression in G space. I'm not going to comment more on that. What it is important then is that we have to solve the Dyson equation for the irreducible polarizability Chi0. Thus, we are not including just a single bubble diagram, but all its geometric series. And as Andrea Marini shown, this is very important. In order to do this and to solve this equation, I will put here just directly the solution. We have to perform a matrix inversion and a matrix multiplication. Once we have the reduced polarizability, we can compute the inverse dielectric matrix and the screened interaction in Fourier space, just with matrix multiplications. It's important to note here that the calculation of the screening is often the most time-consuming part of the computation, and this is mainly because of the computation of the reduced polarizability, which requires an integral over the Brillouin zone, a sum over unoccupied states, and this for each G' matrix element. Then we need also a matrix inversion, and all of this for each momentum transfer and for each frequency we want to compute the screened interaction. So it's a lot of computation. Then it's also important to note here the fact that we need to truncate the basis representation. So, as I said before, we need to compute this matrix elements on a finite matrix, so we need to cut off the number of plane waves. And also we need to truncate the sum over unoccupied states. And this means to have only a finite channel of excitation in this that is an electron hole excitation. So we are not considering all the possible excitations, which are an infinite number, but we truncate this channel up to a certain point. Then, of course, we have to converge this integral here with respect to the discretization of the Brillouin zone sampling. Once we have computed the screening, the next step is to compute the self-energy. Here we have the Feynman diagram represented in the Kohn-Sham space. Thus, we have an incoming Kohn-Sham state labeled with a band index and k-point index, which scatters. And then we have an interaction line, which is the screened interaction W, which brings some momentum and energy. Then we have also an intermediate state described with this G0 that is in a band index M, and it brings a momentum k minus q due to momentum conservation and an energy omega. So due to the fact that in Feynman diagrams we have to sum over all possible paths, this is converted into a sum over all possible intermediate states, an integral over the momentum transfer, and this integral over energy, which is the most difficult part. Then again, we have to represent the screened interaction, in this case, in the Kohn-Sham basis representation by changing the representation with the matrix element I've shown you before, while the G0 is diagonal in the Kohn-Sham space. So in order to proceed with this calculation, and mainly in order to perform analytically the integral over the energy, the screened interaction can be divided into two parts. So the bare interaction and the correlation part of the screened interaction, which represent the response of the system. Due to the fact that the self-energy is linear with respect to W, if we split W into two parts, we have two contributions to the self-energy. So the first one is the exchange part and corresponds to the Hartree-Fock self-energy, in which the self-energy integration is performed trivially due to the fact that the bare interaction is not frequency dependent. While for the correlation part, we can use, for example, the plasmon pole approximation, as was described in the previous talk. In this way, we can, again, have an analytic integration of the correlation part of the self-energy with respect to the energy. Okay, these are the final formulas once the integral over energy is performed. We can see here that, of course, the correlation part of the self-energy will depend on the plasmon residue and on the energy of the plasmon pole, and that, of course, due to the fact that we model each GG prime Q element of the screened interaction with the different pole, this residue and pole depends on GG prime and Q. We can see that here we have the sum over plane waves, as we have seen before. Thus, we have to converge with respect to this finite truncation, and also we have a sum over M, which is the intermediate state of this propagator here. Then again, to truncate the number of Kohn-Sham states means that we are considering just a finite number of possible intermediate states for this G0. Then again, we have to converge with respect to this discretization of the Brillouin zone, which means to discretize the possible momentum transfer here. And we are going to see that for 2D systems, this convergence here is very important and not trivial to reach. Okay, so this is more or less the first recap. the G0 W0 method in one slide. So it's kind of a lot of equations, but not too much. Well, just to remember that we start from a DFT that brings us to the Green's function of DFT that is diagonal in Consham space. Then we have to compute the electric properties, which brings us to the screened interaction in G space. Then to evaluate the self-energy. And to evaluate the self-energy at two frequencies gives us the quasi-particle correction, then the quasi-particle energy within the Newton approximation. Thus, to conclude, the main approximations are that we are neglecting vertex effects, and this brought us to the GW plus RPA. We are neglecting also the self-consistent solution of G, and this brings us to the G0 W0. Then we are approximating the quasi-particle orbitals with the Consham orbitals. We have employed the plasmon pole approximation, and we solved the quasi-particle equation with the Newton method. These are the main approximations in a practical G0 W0 scheme. And the main convergence parameters are the number of plane waves, usually controlled with an energy cutoff, as in quantum espresso, and the number of Consham states included in the calculation of the chi-naught and on the self-energy, and the finite sampling of the Brillouin zone. There are then other minor parameters which should be kept under control, but these are more technical, and they also depend on the system you are considering. So this is the end of the first part. In this second part, I'm going to consider how to perform a G0 W0 calculation for a 2D material. We're going to see that there are some technicalities which should be taken into account in order to obtain meaningful results. First of all, just a definition of what a two-dimensional system is for us, like for the case of graphite that becomes graphene, okay? That is like the most famous two-dimensional system. We have that the two-dimensional system is periodic in two directions, for example, x and y, while it is nano-sized in the third direction, which is not periodic. In this presentation, we are going to focus ourselves on monolayer materials, but the same reasoning holds also for n-layered materials, and also surfaces which are not periodic in one direction can be treated with the same scheme. Finally, also extensions to the 1D case is more or less straightforward, because in this case, the only difference is that we have two dimensions that are not periodic and one that is periodic, but it's not like super straightforward, so more or less. So just a brief introduction about two-dimensional monolayers. As I said, the most famous is probably graphene, that is a semi-metal with Dirac cones, that is composed of a monolayer of carbon atoms, which are in an hexagonal lattice. Then, if you have that the two atoms in the sublattice are different atoms, you can have something like HBN, which is a high-gap insulator that is usually employed as a layer spacer in the systems which are compositions of 2D monolayer materials. Then we have transition metal dechalcogenides that are composed on one plane of transition metal and two planes surrounding of dechalcogenides, and this can be both semiconductors or metals, despite their chemical composition. Finally, we have phosphorine, which shows a peculiar structure, and that it is studied because its electronic properties changes dramatically despite the number of monolayers which are interacting in your system. Okay, so if we want to describe a monolayer material or a two-dimensional material with a plane wave code like quantum espresso or Yambo, that employs 3D periodic boundary conditions, we can use the supercell approach. The supercell approach is quite direct and says that if you have the bulk, but you want to describe the electronic structure of the monolayer, just increase the unit cell in the non-periodic direction, that is L in this case, and at a certain point, the monolayers will not interact anymore. So you add some space up to convergence with respect to L. If you go to a convergence, then you have the electronic properties of the monolayer. But let's see how this convergence is. For the case of the DFT with local or semi-local functionals, everything is kind of easy. For example, just add 2 Armstrong of vacuum with respect to the bulk, gives the converged gap with respect to the amount of vacuum. And this is because the interaction between electrons with local or semi-local functionals is not long range. For G0 W0 calculations, it is the opposite. So we have a long range interaction, and we can see here that the convergence with respect to the amount of vacuum is very painful due to several reasons. First of all, because this is interconnected with the convergence of the Brillouin zone. Then because we need really a lot of space between the layers. Here we have like 60 Armstrong. And it is important to remember that the computational cost scales as L to the 3rd power. Then you have probably to extrapolate the value for an infinite layer separation. And finally, we have also that vacuum states are deeply affected by the amount of vacuum. Then you have to keep in mind that all these lines require a convergence with respect to unoccupied states. So due to this, it is like evident that to remove the interaction between the replicas, the strategy to add a lot of space between the monolayers is not a successful strategy. Then we need to explicitly cut off the interaction. And this is done in this way. So this is the bare Coulomb interaction that in reciprocal space is 1 over r, simply, while in Fourier space is 4 pi over q squared. What we want to do is to truncate the Coulomb interaction between the replicas of the monolayers. This is done in a real space with a Heaviside theta. And in this way, each electron does not see anymore other electrons which are plus or minus L halves distant in the non-periodic direction. So this electron here sees only other electrons in this place here. Thus, we are removing the interaction between electrons that are near to different monolayers. If we perform the Fourier transform of this expression here, we found this expression here, which is the one that should be used instead of the bare Coulomb interaction. We can see here that in the long wavelength limit, we have a different power law. Okay, and this will change the dielectric properties. So again, if we look at the G0 W0 formulas in one slide, we can see that to change the interaction, change more or less all the formulas, because of course the Coulomb interaction is one of the main ingredients of a G0 W0 calculation. We focus on the dielectric properties, thus on the inverse of the dielectric function. And here we can see for MOS2, for the case of 20 Armstrong of vacuum, the difference of the head of the dielectric function, thus the GG prime equals 0 component, for the static dielectric function with respect to the momentum transfer, the difference between the case of a truncated interaction and an untruncated interaction. It can be seen here that for medium to high wave vectors, the response of the system is the same, while in the long wavelength limit, the two responses are qualitatively different. While for the case of the truncated interaction, epsilon minus 1 goes to 1, and this means that there is no screening in the long wavelength limit, if you do not cut off the interaction, you end up with a finite value. And this can be described with this cartoon here, in which we imagine to have an electron and a hole, and we consider the screening between them. So long wavelength limit means that the two charges are very far away one to the other. And in a three-dimensional material, if you have that these two charges are very far away, due to the fact that the material covers all the 3D space, you still have macroscopic screening. While for a 2D monolayer, if you put the two charges very far away, due to the fact that the material is nano-sized in one direction, the vast majority of field lines travels into vacuum. And this means that in the long wavelength limit, these field lines are all in the vacuum. Thus, there is no screening. Thus, we end up with the fact that if we do not include the truncated interaction, we are changing qualitatively the description of the screening with respect to the truncated case that is the physical one. But here we can see that we added kind of a very sharp behavior of the dielectric response in the long wavelength limit. And we can imagine that this will, so that it will be very difficult to converge these dielectric properties with respect to the Brillouin zone sampling. And this we'll see in the next part of the presentation. So here we can see the convergence of the quasi-particle gap for three prototypical semiconductors with respect to the number of key points of the Brillouin zone. And it can be seen here that very dense Brillouin zone samplings are required in order to obtain convergent gaps. This is a general property of two-dimensional semiconductors. This is a general properties of two-dimensional semiconductors like these three. As we can see here, this behavior originates from several reasons. First of all, to this sharp behavior of the G prime equals 0 element of the dielectric function, of the inverse dielectric function. Then also those matrix elements which are orthogonal to the periodic directions are quite dispersive. And here we can see the dielectric function obtained with a fine grid, the 60 times 60, which are circles, compared with squares that is obtained with a coarse grid, this is 6 times 6, and it can be seen that this dispersion cannot be followed with a coarse grid. Then we also have the problem that due to this behavior of the inverse dielectric function that goes to 1 in the long wavelength limit, this means that the correlation part of the response of the system goes to 0, while the divergence of the slab of the screen of the bare interaction, then we have a multiplication of 0 times infinity, which can generate some numerical problems for this point here. Thus, in order to accelerate the convergence of these quasi-particle properties with respect to the Brillouin zone sampling, some attempts have been done in the literature. How many time do I have?
Not much.
Okay. So, okay, these are two possibilities, but I'm gonna explain during the last part of the talk which is the one that is implemented in the Yambo code and that we derived. So here the scheme, so our goal is to compute the quasi-particle corrections, and this means to compute the self-energy. So we can split the self-energy into two parts, the exchange and correlation, and for example, we start from the exchange part that is easier, And the integral over momentum transfer is usually transformed into a discrete sum. So what is done in Yambo is, instead of using the numerical value of the interaction in the finite discretization, is to use the average value of the around the discretization domain, as can be seen here, in which we have a discretized Brillouin zone. These integrals are performed with a Monte Carlo integration, and this is possible due to the fact that we know the analytic form of the Baire interaction. And this is usually done for a finite number of g's, because for I modulus g vectors, to perform this average is useless due to the fact that this function becomes smooth. So our idea to accelerate the convergence is to apply the same scheme also to the correlation part of the self-energy that is now proportional to the correlation part of the screened interaction. The integral is again performed with the Monte Carlo method and is applied on a submatrix Gg prime up to a certain value G lim. But now we don't have the analytic expression, an analytic expression which can be like computed 1 million of times in order to compute the integral with the Monte Carlo method. Thus the procedure is this one. First of all, we write the correlation part of the screening interaction in this way in terms of an auxiliary function. Then we interpolate the auxiliary function between the numerical point and its nearest neighbors in reciprocal lattice units. Here we can see briefly the results of this interpolation. On the top panels, this auxiliary function, and on the lower panels, the screened interaction for some selected matrix elements. The first thing we can see is that we have that the screened interaction changes its order of magnitudes, while the auxiliary function do not. And this is why it is better and more stable to interpolate the auxiliary function instead of the screened interaction. Then we can see that the accuracy of the most important point that corresponds to the long wavelength limit is accurately described due to the fact that we have explicitly including the analytical trend of the auxiliary function. Thus, we have used a particular expression for this case. Looking at the results for the gap, we can see that for the case of MOS2, even the first, so the Corsair grid, is sufficient to obtain convergent gaps. And with convergent gaps, here I consider an error of 50 millielectron volt with respect to the extrapolated value at an infinite sampling of the Brillouin zone. And it can be seen here that the extrapolation is justified also by the fact that these two methods converge to the same value, to the same extrapolated value. Again, also for phosphorine, we can see that we can use a very coarser grid like the 8 times 20 times 1 instead of this 36 times 50 grid, thus saving a lot of computational time. And the same is true also for HBN, in which we can use the 6 times 6 instead of the 36 by 36. It's important to notice here that the computational cost scales as the fourth power of this number here, because it scales at the squared of the total number of key points. So the total number of key points in this case is 6 times 6, 36 squared. So to conclude, there are three technicalities that should be taken into account in order to simulate a two-dimensional system. The first one is the supercell approach. The second one is the cutoff of the potential. And the third one is this W-averaging method that speeds up the convergence with respect to the number of key points. So with the combination of these three techniques, we are able to treat non-periodic systems with a plane wave basis set, to use an amount of vacuum which is not too large, like from 10 to 20 Armstrong for the case of monolayer, and to converge the quasi-particle properties with grids which are comparable with density functional theory calculations. A brief note that these techniques, this seems to like to speed up, but in most of cases, it makes the difference between a calculation that you can or you cannot done. Thus, these are more or less mandatory. Very soon after the paper of this method is published, I'm gonna add a tutorial dedicated for the G0, W0 of these two-dimensional systems, but unfortunately not in this school, mainly because the paper is under the process of submission. Thank you for your attention.
So, thank you, Alberto. Just a couple of announcements before we open the session for questions. After lunch, we are going to have the poster session, which will be a virtual poster session. I think there are 3 of you here who prepared a poster. So remember that you are supposed to do a 1-minute presentation, and you should have just received an email with instruction on how to handle the poster session. And then, due to the poster session, we are not going by walk to the canteen. There will be a shuttle just outside the ICTP. Actually, we are supposed to leave now, but we take a few more minutes to address the questions, and then we go. So, questions?
Yeah, thank you very much for the talk. And I see the question about the truncation of this Coulomb interaction for the 2D system. And for some 2D system, like you have shown here, which are periodic in just one dimension, so it's very easy because the periodicity is very easy to handle. But there are some systems, there's some 2D systems that are very large in this dimension. How do you handle the truncation in this case, or is it general?
So let's suppose to have like several monolayer materials with a huge space. Is this true, right? So this is the case you were talking about. Well, in that case, this method is not so efficient because, of course, you need in your cutoff to include the interaction you want to include. For example, if you have a very so if you have several monolayers, then this cutoff, so this L should be still quite large. But in any case, you restore the qualitative behavior of the dielectric response, and this is still very helpful. Then, of course, the bigger is your system, the more computational time you need, and this is a little bit less efficient because you have to truncate between different layers, but do not truncate within the layer. And this ends up with a very like general rule, but not so accurate, that you need at least as a vacuum the thickness of your slab plus something. Like for the monolayer, for MOS2, it's like 10 Armstrong. If we have something that is like with a thickness of 10 Armstrong, so a very general rule is that maybe 20 Armstrong can be sufficient. But then, of course, you have to converge. Because in this case, you have like an electron that is in one side of the monolayer. That is, so he needs to see more or less so the electron on the other side of the monolayer, but he needs not to see the first electron of the replica.
Okay, we have another question here.
So in the expressions, I mean, like when you're computing the W, so you have some terms with rho. If I'm not wrong, they are the dipoles, right? And the very beginning. Yes.
Okay, so
the rho, they are the dipole.
Yeah, so I think here.
Yeah.
Okay. These are the generalizations of dipoles. So their expression is this one. Okay, so maybe I can point here so you can see. So these are these expressions here, which are the matrix elements to change from the base of Kohn-Sham states to the base of plane waves. And for Q that tends to 0, you can see that these are the dipoles, because, well, this more or less becomes R. It can be seen, R times Q. Okay, then the mathematics should be done in a proper way. But this is the final result. So for Q that tends to 0 and G equals 0, these are the dipoles. But then we need also these elements for Q and G different from 0. And yeah, this is the expression that I think is one of the most unknown expressions within the Yambo code, because it depends like on K, N, M, Q, and G. Then so these numbers here are...
This is one of the most demanding part, computational part, and it's used in many steps. Yeah.
But like the physics is trivial, so just to change from one base to the other.
Yeah, so I don't know, I mean, like, could you please justify why your plasmon, I mean, like, for example, if you take, I mean, this is related, somewhat related to the previous talk too, why your like choice of your poles, plasmon poles, is independent of your thing. So here you are taking some, I think, if I remember correctly, it's 1 Hartree or something you're using. So why is it independent of the choice of this thing? Also, like, I don't know, I mean, like, the poles of this W are basically the plasmon energies, right? So which are the, like where the dielectric tends to 0. But how do you compute those values? I mean, like, how do you compute the poles of the inverse of the dielectric tensor? So
okay, so, well, in this lecture here, it was mainly on the practical equations and approximations. So here I just explained that with this plasmon pole approximation, which is the standard procedure, this is why I take the plasmon pole approximation as an example, because the main goal of this part of the lecture was like to show the equations of what is the standard. And plasmon pole is standard. Then you have that the approximation behind the plasmon pole is that if you consider the macroscopic case, thus Gg prime equals 0, then you can see that this experiment of a lot of materials is more or less you see more or less one plasmon. Then you can see, okay, with Gg prime different from 0, that is the microscopic response, you change the residues, but the non-interacting poles are the same. Then you can say, okay, we can approximate and say, okay, there is just one pole also in the other matrix elements of the microscopic response. This is, of course, an approximation, justified by the fact that the more these G modulus are higher, the less important is the response of the system. Okay,
I think it's time to go now, because there is a shuttle waiting for us. And as yesterday, you can leave your things here if you want. We are going to lock the room. Okay.
Yeah, just as a final remark, that if someone wants to ask a question, you can ask me in person.
Yeah, I think during the tutorials, yeah.
Yeah, during the tutorials.